Next is perpendicular polarization. So as we define that the perpendicular polarization is the polarization in which the electric field is perpendicular to the plane of incidence. So we have to make a diagram in such a way that the electric field of the incident plane wave should be perpendicular to the plane of incidence. So as we consider in the parallel polarized wave, the plane of incidence is x of xz and the boundary is z equal to 0. So let us consider the same figure. The only difference is the boundary and electric field. The only difference we have to make is that we have to make in such a way that electric field should be perpendicular to the plane of incidence. So this is medium 1 and medium 2. So this is medium 2 and this is medium 1. So wave is incident from here. This is the Ki and the wave is reflected here. This is Kr, reflected propagation vector, and this is the transmitted propagation vector Kt. Now we have to make the electric field in such a way that should be perpendicular to the plane of incidence. So let us consider the electric field in this direction. So it is outside the board and it is the direction of propagation. So what should be the direction of magnetic field? So the direction of magnetic field is always considered as AK cross AE. So it should be, this is the direction of propagation, and if I curl finger from here, because it is the outside the board, so if I curl finger from the direction of electric field to the magnetic field which is outside the board, so this is the direction, so this thumb is pointing in this direction, it means that the direction of magnetic field should be here. So this will be the direction of magnetic field HI, and this is EI, this is EI. Now by default we are assuming that the electric field is having the same direction as incident wave. So if we assume this, then we have to make this in this direction. So what should be the direction of magnetic field? This is the direction of electric field, and we have to take the cross product from the direction of propagation to electric field. So again it should be like this. This is the direction of propagation and electric field is outside the board. So this is the outside the board. Let us consider in this way. This is the outside the board. So if I consider this, I curl my finger from this to this. So thumb is pointing in this direction. It means that this would be the direction of magnetic field. So this is HR and it is ER. Now we know that this is the angle of incidence theta I, this is the angle of reflection theta R. So if this is theta I, it is alternate angle, so this is theta I. So this is also theta I. If this is theta R, then this should be theta R and this should also be theta R. So this is theta T, and we know that the direction of incident wave and transmitted wave will remain same. So the direction of electric field is outside the board. So here also this would be the outside the board, that is ET, and this would be the direction of magnetic field HT. And if this is theta T, so this is theta T, and this will be 90 minus theta T, so this will be theta T. So now we have consider all the angles and direction of electric field and magnetic field. Now we have to write the incident wave and the reflected wave and transmitted wave, and have to derive the equation of reflection coefficient for parallel perpendicular polarization and equation of transmission coefficient for perpendicular polarization. So let's write equation for incident wave. Incident wave. Now the incident wave, this electric field is in which direction? So this is x and this is z. Then we know that according to the coordinate system, the outside the board will be the y-axis. So outside the board will be the y-axis. So positive y-axis. So electric field is having the positive y direction. So we know how to write EIS, suppressing the time factor. The peak value is EI naught. It is having the y component, so AY. Now e to the power minus j. Now we have to calculate Ki dot r. So this Ki we have to write incident propagation vector. What would be the incident propagation vector? So this incident propagation vector magnitude is beta 1, because now we are talking about the medium 1. So the magnitude of incident propagation vector is beta 1, and the cos component will go into the z direction and sin component will go into the x direction, but means both are positive. So beta 1 cos theta I in z direction and beta 1 sin theta I in x direction. And we know that the r will be same, x ax plus y ay plus z az. So the dot product would be the x component multiplied with the x variable and the z component multiplied with the z variable, because az dot az will be 1. So we know that the direction of the incident wave should be multiplied with that variable, will become k dot r. So now e to the power minus j k dot r, that means x beta 1 sin theta I plus z beta 1 sin theta r. This is equation number 1, incident wave. Now we have to write the magnetic field equation. So magnetic field is HIS equal to, the peak value is HI naught. Now let's resolve this magnetic field, because this magnetic field is having the two components. So the cos component is in the negative x direction. You can see that this is the magnetic field direction and this is the cos component. It is moving in the downward direction and it is showing the positive direction, sin component. So the cos component is in negative x direction. So the cos theta I in the negative x direction and HI naught sin component is in the positive z direction. So this is the value of magnetic field components. Now because we are talking about the incident wave, so incident propagation vector will remain same. So e to the power minus j x beta 1 sin theta I plus z beta 1 sin theta r. This is equation number 2. This is all about the incident wave. And because we write this HI naught in terms of electric field, so let's not write equation number 2 and let's change this peak magnetic field in terms of electric field. So in terms of electric field, this HI naught is common. So we can write this EI naught divided by eta 1, and in bracket we have got minus AX cap cos theta I plus sin theta I AZ cap in e to the power minus j x beta 1 sin theta I plus z beta 1 sin theta r. This is equation number 2. Now let's write for the reflected wave. The difference between the incident wave and reflected wave is nothing but the coefficient will remain same and the direction we have to change for the propagation vector, right? So let's write ERS for the reflected wave. Now, as we assume that the reflected electric field is also having the plus Y component, so this ER naught, which is the peak value, and AY cap. So this is the electric field peak value and its direction. Now e to the power minus j and the propagation vector, right? So k dot r. So this kr, magnitude of kr is beta 1 because we are talking about the medium one. Incident wave and the reflected wave both will be in the medium one. So the magnitude of kr is beta 1 and the cos component is in the negative z direction. So the direction is z, so it should be multiplied with the variable z. Okay, so here if you write, this would be beta 1 and the angle it forms is theta r, so cos theta r, and it is in the negative z direction, so it should be multiplied with minus z. Okay, now plus beta 1 sin theta r, and the sine component of this kr is in the plus x direction, so the direction is x, so the variable multiplied should be x. So the variable multiplied is x here. So this is equation number 3. Now we have to write the magnetic field. So magnetic field is HRS equal to. So now we have to resolve the magnetic field, and this magnetic field is the cos component. The cos component here is in the plus x direction, and the sine component here is also in the plus z direction. So this is plus z direction, this is plus x direction. So we are having HR0 cos component in the plus z direction, so cos theta r a z cap, and HR0 sine component in plus x direction ax cap. And the direction of propagation vector will not change for the electric field and magnetic field, both will remain same. So this is beta 1 cos theta r with minus z multiplied and beta 1 sin theta r multiplied with x. This is equation number, we will not write equation because again we will write in terms of electric field. So the electric field would be ER0 divided by eta 1, this is common, and cos theta r az cap plus sin theta r ax cap and e to the power minus j in bracket beta 1 with minus sign here cos theta r into z plus beta 1 sin theta r into x. This is equation number 4. This is all about the reflected wave. Now let us write for the transmitted wave. The transmitted wave is ETS, suppressing the time factor, ET0 peak value, and same as in the direction of incident wave. So the direction of transmitted wave and incident wave, and even in reflected wave here it is same. So this is plus y, so ET0 plus AY I have written, and the propagation vector is now cos component is in the plus z direction, sine component in the plus x direction, both are positive, and z and x direction, so it should be multiplied with the variable z and x. So e to the power minus j in bracket, it is beta 2, because now the propagation vector has the magnitude equal to the phase constant of the second medium, so that is beta 2 cos of theta t into z direction and beta 2 x sine component sine theta t x direction. So this is equation number 5. Now HTS. So now we will write the peak value directly in terms of eta. Okay. So now the magnetic field is cos component in the negative x direction, sine component in the plus z direction. You can see this is the cos component, and this cos component is going in the negative x direction. This is negative x. This is in the minus x direction, and this is the sine component which is in plus z direction. So ET0 divided by eta 2, this is the peak value, cos component theta t in the negative x direction plus Et0 divided by eta 2 sine component in positive z direction, and this exponential term e to the power minus j, because the propagation vector will not change, so the k dot r will not change. This is beta 2 cos theta t into z plus beta 2 x sin theta t. This is equation number 6. Now we have written all the 6 equations. So the use of this diagram has been finished. Now we can rub it, and we have to calculate, or we have to apply the boundary condition. And what the boundary condition says that the tangential component of electric field and the tangential component of electric field in medium 2 both are same. The tangential component of the tangential component of electric field in medium 1 is equal to the tangential component of electric field in medium 2. So what is the tangential component? And we know that the boundary is z equal to 0. So as we consider in the case of parallel polarization, the component which is in the direction of z, that will be the normal component, and the remaining, that is x and y, will be the parallel component. So here in the electric field we are having the y component, it means that is a tangential component, and in the magnetic field we are having the x component and z component, and the component which will be in the z direction will be the normal component. So this is the normal component and this is the tangential component, and electric field is again having only the y component, so it is the tangential component, and magnetic field is having the z component and x component, and z component is normal component and x component is tangential component. And for the transmitted wave as well, this is the tangential component and this is the tangential component, and this would be the normal component. So we have got all the tangential and normal component of medium 1 and medium 2, and we know that the tangential component in medium 1 is the tangential component of incident wave and the tangential component of reflected wave. Okay. So let's apply the boundary condition for electric field first. Boundary condition: at z equal to 0, tangential component of medium 1 is equal to tangential component of medium 2, and in medium 1 there are two waves, one is incident and another one is reflected. So the incident wave at z equal to 0 of electric field. So incident wave at z equal to 0, it means this term will vanish. So we will have only this term ei0 e to the power minus j etc. So that is ei0 e to the power minus j x beta 1 sin theta I. This is only for the incident wave, and in medium 1 we have incident as well as reflected wave. So the reflected wave is having tangential component only. So at z equal to 0 means this term will vanish, and er0 e to the power minus j beta 1 sin theta r into x. So that is plus er0 e to the power minus j beta 1 sin theta r into x equal to, this is the total electric field in medium 1, those are tangential. Okay. So those are tangential we have written. Now we have to write the tangential component of medium 2. So the tangential component of medium 2 we can calculate. In the medium 2 we have only one wave, which is transmitted wave. So it is tangential component, that is at z equal to 0 again. So if you put z equal to 0 here, then et0 e to the power minus j and this one et0 e to the power minus j beta 2x sin theta t. This we have got. Okay. Now after this, the equation is very simple. We have to apply this two relation, theta is equal to theta r, and also beta 1 sin theta I is equal to beta 2 sin theta t. This we have to apply. Okay. So let's write here this is EI0 e to the power minus j x beta 1 sin theta I plus ER0 e to the power minus j beta 1 theta r is equal to theta I, so this is theta I into x equal to ET0 e to the power minus j beta 2x sin theta t. So this is also e to the power minus j beta 1 x sin theta I, e to the power minus j beta x sin theta I. So this exponential term is common, so this exponential term, this exponential term and this exponential term will be cancelled according to this. So now we have got this EI0 plus ER0 equal to ET0, and if I divide it by EI0, then I will get 1 plus ER0 divided by EI0 equal to ET0 divided by EI0, and the reflected wave divided by incident wave gives the reflection coefficient for perpendicularly polarized wave, and this is the transmitted wave divided by incident wave gives the transmission coefficient for the perpendicular polarized wave. So this is the equation which we have got, and the relation between the transmission coefficient and the reflection coefficient for perpendicular polarized wave. This is the same relation which we have got for the normal incidence as well. So in the normal incidence we had this 1 plus gamma is equal to tau, and in perpendicular polarization also we have 1 plus gamma is equal to tau, but in case of parallel polarization there is no relation in this way. There is 1 plus gamma is equal to tau multiplied with cos theta t divided by cos theta I. So in case of parallel polarization there is no direct relationship, we have some extra term with tau parallel or tau, that is transmission coefficient. Now this is equation number 7. Now we have to find another equation by which we can calculate the reflection coefficient, and that is the boundary condition for magnetic field. So boundary condition for magnetic field is boundary condition for magnetic field. This is HT1 is equal to HT2 at z equal to 0. So the tangential component of magnetic field. So magnetic field equation we are having. So this is the tangential component, and at z equal to 0, that means this term will be 0. So we are having minus sign EI0 divided by eta 1 cos theta I. So minus sign EI0 divided by eta 1 cos theta I e to the power minus j beta 1 x sin theta I. Now the tangential component of this from equation number 4, so at z equal to 0 this term will be 0, and the tangential component is ER0 divided by eta 1 sin theta r. So here there is one mistake that you can correct it. This cos component was in x direction and the sin component was in z direction, okay. That I have done mistake, and you can correct it. So this is the cos component which is x direction and this is in z direction, so this will be changed. Now this will be the tangential component and this would be the normal component. So we have to take the tangential component, so this is ER0 divided by eta 1, so we are writing this plus ER0 divided by eta 1 and the cos component, that is cos theta r, and e to the power, if z is 0, minus j beta 1 sin theta r into x. This is the total magnetic field in medium 1 which is tangential, and the transmitted wave, so we get the transmitted wave and the tangential component, that is this component which is ET0, x component is the tangential component, so this is ET0 divided by eta 2 cos theta t with minus sign, so this is the minus sign. So now this theta I is equal to theta r, so this theta r should be replaced by theta I and also the exponential term. So let's clear it and then we will write. Consider these two, theta is equal to theta r and beta 1 sin theta is equal to beta 2 sin theta t. So minus ei0 divided by eta 1, this is cos theta I, that is cos theta I e to the power minus j beta 1 x sin theta I, and it is plus er0 divided by eta 1 cos theta I e to the power minus j beta 1 sin theta I into x equal to minus et0 divided by eta 2 cos theta t. And yes, the exponential term was also here. So this is e to the power minus j at z equal to 0, so this term is 0, e to the power minus j beta 2x sin theta t is also there, and this is e to the power minus j beta 2x sin theta t. And when you apply beta 1 sin theta I is equal to beta 2 sin theta t, this exponential term will vanish, and also the taking the minus sign common, then this minus sign will be cancelled and this will be the minus sign in between these two. So we are having ei0 divided by eta 1 cos theta I, and I have taken the minus sign common, so this is er0 divided by eta 1 is equal to, and the one more term is here, that is cos theta I again, and it is equal to et0 divided by eta 2 cos theta t. So if I take this ei0, this cos theta I and divide by eta 1 common, then it is ei0 minus er0 is et0 and eta 1 divided by eta 2 and cos theta t divided by cos theta I. If I again divide it by ei0, then what I will get, ei0 divided by ei0 minus er0 divided by ei0 equal to et0 divided by ei0 eta 1 cos theta t divided by eta 2 cos theta I. So ei0 divided by ei0 is 1. This is the reflection coefficient for perpendicular polarized, this is the transmission coefficient for perpendicular polarized, and this is eta 1 cos theta t divided by eta 2 cos theta I. This is equation number 8. So this is the two equation which we have got, which we were looking for. Now this is 1 minus gamma, this is 1 plus gamma. On adding equation number 7 and 8, we can have the value of reflection transmission coefficient, and from equation number 7 we can get the value of reflection coefficient after getting the transmission coefficient. So on adding equation number 7 and 8, we get 2 equal to tau perpendicular is common, in bracket eta 1 cos theta t divided by eta 2 cos theta I plus 1, and when we take the LCM we get tau perpendicular is equal to 2 eta 2 cos theta I, which is same as the parallel transmission coefficient, numerator is same, but in the denominator eta 2 and associated angle is of the medium one, that is angle of incidence, which is eta 2 cos theta I plus eta 1 cos theta t. In that case, I told you that how to remember the formula, that is if the medium is second, then the angle associated will be the angle of second medium, that is theta t. But in case of perpendicular polarization, if the medium is second, then the angle associated with the term eta 2 is the angle of incidence, that is angle of first medium. So eta 2 cos theta I and eta 1 cos theta t, and in the numerator that is same as the in case of parallel polarization. Now the tau parallel we have got with the help of equation number 7. By subtracting with minus 1 we can get the reflection coefficient, and the value of reflection coefficient for perpendicular polarized is 2 eta 2 cos theta I divided by eta 2 cos theta I plus eta 1 cos theta t minus 1. We have to subtract it. So when we subtract it, this gamma perpendicular is 2 eta 2 cos theta I minus eta 2 cos theta I minus eta 1 cos theta t, and whole divided by eta 2 cos theta I plus eta 1 cos theta t, and this gamma perpendicular is this 2 eta 2 and this eta 2 will get cancelled and we get eta 2 only. So eta 2 cos theta I and eta 1 cos theta t divided by eta 2 cos theta I plus eta 1 cos theta t. So this is the perpendicular polarized reflection coefficient. So now we will again consider the Brewster angle. So you can take a pause here and you can revise that what we have derived. So now it is easy for you to write the equation from the diagram given, whether it is a parallel polarized or perpendicular polarized. So what is the Brewster angle? So we know the Brewster angle is defined as the angle of incidence for which the reflection is 0. So the reflection coefficient becomes 0 at which angle? So the Brewster angle when theta I become theta b perpendicular, because we are defining it for the perpendicular polarized wave, theta b perpendicular, this gamma perpendicular becomes 0. So gamma perpendicular becomes 0 when eta 2 cos theta b perpendicular is equal to eta 1 cos theta t. When this condition will be satisfied, then the reflection coefficient becomes 0, and after the calculation again we get this theta b perpendicular is equal to sine inverse of root over 1 minus mu 1 by mu 2 and epsilon 2 upon epsilon 1 divided by 1 minus mu 1 by mu 2 whole square. This is the formula. After deriving, we are not deriving it here. Now, if both the medium are non-magnetic, then mu r1 equal to mu r2 equal to 1, and this equation will become theta b perpendicular is equal to sine inverse of root over 1 minus, this is mu naught mu r1 divided by mu naught mu r2 and epsilon naught epsilon r2 divided by epsilon naught epsilon r1 whole divided by 1 minus mu naught mu r1 divided by mu naught mu r2 whole square. So when you substitute mu r2 equal to mu r1, after solving this we will get sine inverse of root over, this is 1 minus this mu naught epsilon naught will get cancelled and we get mu r1 epsilon r2 divided by mu r2 epsilon r1 whole divided by 1 minus mu r1 divided by mu r2. Now we are saying that if both the medium are non-magnetic in nature, then this value is equal to 1, and if this value become 1, so this will be the sine inverse infinite. This will be the sine inverse infinity, which is not possible. We know that this sine inverse infinity does not exist. So that is why, since this sine inverse infinity does not exist, is invalid, Brewster angle for perpendicularly polarized wave, perpendicularly polarized wave does not exist. Okay, so this is the important point, that for a parallel polarized wave the Brewster angle exists, and for perpendicular polarized wave Brewster angle does not exist. So whenever the medium is lossless, so I told you in case of when we were discussing the wave propagation through a different medium, then practical lossless mediums are generally non-magnetic in nature. So whenever we study the lossless medium, we study about the non-magnetic lossless medium. So if the practically only non-magnetic lossless medium is present, it means that the Brewster angle will not exist for them. So Brewster angle will not exist for lossless non-magnetic medium, and hence when the wave is incident with the angle of Brewster angle, that means that if the reflected wave is also present, it means that it has to be perpendicular polarized only, because the perpendicular polarized wave cannot be cancelled, because for the perpendicular polarized wave there is no angle of incidence for which it can have the value 0. So reflected wave will be present when the wave is perpendicularly polarized. So because the reflection coefficient is not 0, there is no such angle which make the reflection coefficient 0, especially for non-magnetic lossless medium. So that is why we said that when the incident wave is having both the components, parallel component and perpendicular component, and if the angle of incidence is equal to the Brewster angle, then the reflected wave is definitely be perpendicularly polarized, because the parallel polarized waves are cancelled, because for the Brewster angle the reflection coefficient is 0 for parallel polarized but not for the perpendicular polarized. So if the reflected wave is present, then it has to be perpendicularly polarized. So this is all about the perpendicularly polarized wave, and if you want to consider that there is a non-zero value and epsilon r1 equal to epsilon r2 equal to 1, then you can consider this tan theta b perpendicular is equal to root over mu r2 upon mu r1. This we can consider from here if we assume epsilon r1 equal to epsilon r2 equal to 1 and mu r1 is not equal to mu r2, mu r1 and mu r2, mu r1 and mu r2 are not equal to 1, are not equal to 1. So if this is the case, then you can have this formula, because this when you consider these two as 1, so this will be cancelled, and after that the same calculation we did for the parallel polarized, and in the end we get epsilon r2 upon epsilon r1 in case of parallel polarized. In case of perpendicular polarized we get mu r2 upon mu r1, but this is not a practical value, so we can calculate this theoretically only. But if we talk about the questions and if we talk about the practical values, so all the lossless mediums are practically non-magnetic in nature, and if they are non-magnetic, then mu r1 equal to mu r2 equal to 1, and the sine inverse infinity we will get, which is not existing. So that's why the Brewster angle will not exist in case of perpendicular polarized wave.